Yesterday we talked about three types of forces. Right, there's the net force, which is the sum of all the forces, the total of all the forces. But what forces are we talking about that we have to add together? Well, the first one was the weight. The first force was the weight. We defined weight as what? The force of, right, force of gravity acting on an object. Let's differentiate that with mass. Okay, force and mass are two different things. Mass is the amount of matter that something possesses. Okay, it's how much, essentially, the number of atoms, basically, that something possesses. And that's going to be the same no matter where you are in the universe. My mass is 70 kilograms. It doesn't change. Here, on the moon, on Mars, wherever I go, it's 70 kilograms. But my weight does change because it's the force of gravity. And the force of gravity is dependent upon the acceleration due to gravity. The acceleration due to gravity on Earth, it varies a little bit depending upon where you are, but for the most part, it's around 9.81 meters per second squared. A little bit higher in Vancouver, a little bit lower at the top of a mountain in Banff, let's say. The next force that we talked about was the normal force. You guys remember what that word normal means in physics? Yep. Good. It means 90 degrees. So a normal force is the force that acts at 90 degrees. 90 degrees to what? Usually the ground, right? Although it's not necessarily the ground. Okay, we talked yesterday about a situation where it could be the roller coaster track, right, that provides the normal force. Okay, it's something that is either the ground or takes the place of the ground, basically. Maybe it's the floor of the elevator. Maybe it's the track on the roller coaster. Maybe it's your seat. Okay, as you're in one of those inverted roller coasters. Okay, whatever it is, it takes the place of the ground, and it supplies that force at 90 degrees. Okay, sometimes it's up. Usually it's up. But then sometimes it's at an angle, or sometimes it's even down. The third force we talked about was the friction force. Friction force was that resistive force, resists motion. It wants to keep an object from moving, slow an object down if it's already moving. There were two kinds of friction forces. One was the force of static friction, and the other one was kinetic friction. Static friction was the force of friction that keeps an object from beginning to move, and kinetic friction was that force of friction that tries to slow down an object when it's already moving. That make sense? Which one was a bigger force? Static friction has the potential to be a bigger force. Okay, that's why it's harder to get something moving than it is to keep something moving. Okay? You know that when you push something before, you're pushing that big dresser across the floor in your bedroom. Okay? Pushing it, it doesn't want to move. Once you finally get it moving, now it slides easily because the force of kinetic friction is less than the maximum force of static friction was. Make sense? The final thing we talked about yesterday was free body diagram. A free body diagram is a diagram that shows all of the forces that act on an object. Okay. All of the forces that act on the object include the normal force, the force of gravity, but also include forces like friction, also include forces like the force that you pulled with or pushed with, okay? The force of the wind acting on something, okay? Include all of the forces and draw those arrows roughly the right length, okay? Roughly proportional to how big those forces actually are. Right, Jesse? Today, we're going to talk in more detail about friction. Static friction, as we said yesterday, is the force of friction that prevents an object from beginning to move. Now, what's kind of weird about static friction is that it's not just a constant value. It changes. The force of static friction varies with how hard you push. That's weird. If I push on Tyler's desk with a force of 5 newtons and it doesn't move, then the force of friction pushing back must have been 5 newtons. If I push on it with 10 newtons and it doesn't move, then the force of friction pushing back must have been 10 newtons. If I push on it with 50 newtons and it doesn't move, the force of friction pushing back must have been 50 newtons. So friction, static friction, had the ability to react to how hard I was pushing. Static friction will always be the same value as the force that I'm pushing with until it reaches a maximum value. Make sense? So I push with 5 newtons, static friction is 5 newtons. I push with 10 newtons, static friction is 10 newtons. I push with 50 newtons, doesn't move, static friction is 50 newtons. I push with 51 newtons, and it moves. The maximum force of static friction was 50 newtons. Static friction became however hard I was pushing until I exceeded the maximum value, in that case of 50 newtons. And then, well, it wasn't static friction anymore, then it was kinetic friction. Okay? So it varies with how hard you push until you reach that maximum value, in that case of 50 newtons. It's weird, right? How does it respond to how hard I push? Well, you can't have static friction when no forces are pushing on it, right? I'm not pushing on Tyler's desk right now. There's no static friction acting on it. Static friction has the ability to be a certain value, but it's not going to be a certain value until it has to be, until I push that hard. Kinetic friction, on the other hand, sometimes we call it dynamic friction. Sometimes we even call it, although this isn't very often, we sometimes call it sliding friction. Usually it's kinetic or dynamic. The word sliding, though, does sometimes become helpful to us because it reminds us that, say, the car tires that we were talking about yesterday, right? When they're turning, when the tires are turning on the road, they're not sliding. That's actually static friction. When the tires are sliding on the road, then that's kinetic friction. So again, it reminds us when sometimes when we have kinetic and when we have static friction, it's a more, even though we don't use that term very often, it's sometimes a better term, sliding friction. It's the force of friction that acts against an already moving object. So when I pushed Tyler's desk with 5 newtons, it doesn't move, static friction was 5. I pushed it with 10 newtons, doesn't move, static friction was 10. I pushed it with 50, didn't move, static friction was 50. Pushed it with 51, it did move. Static friction was, at that point, how big was static friction when I pushed it with 51? No. How big was static friction when I pushed it with 50? No, not 50. 0. Why did static friction become 0 when I pushed it with 51 newtons? Yep, because it started moving. What kind of friction do we have now? Kinetic friction, right? Does that make sense? Doesn't mean friction's 0, right? Okay, it doesn't mean friction's 0, but static friction is 0 because it would all be kinetic friction there. Now, the force of kinetic friction is normally lower than the maximum force of static friction. Doesn't mean it's lower than the actual value of static friction, but lower than the maximum value of static friction. So again, I pushed Tyler's desk with 51 newtons, it starts moving. Well, maybe kinetic friction, once it starts moving, is 35 newtons. 35 newtons is lower than the maximum value of 50 that Tyler's desk had. But it's not lower than the 5 that I pushed with the first time, or the 10 that I pushed with the second time. It's just lower than the maximum possible value of static friction, the 50 newtons, that when I exceeded began to move and turn it into kinetic friction. Let's take a look at a couple equations, or, well, kind of equations. Let's give you the equation for the force of kinetic friction first, because it's easier. The force of kinetic friction, we'll call it FKF. I'm going to put little absolute value signs around that. What does that mean? Little vertical lines, absolute value signs. Yeah, Abby? Yeah, we're going to make it a positive value. In other words, whatever value that we find won't tell us which direction kinetic friction is acting. It'll just tell us the value of it, the magnitude of it, right? And that's okay, because we can determine by some other means what direction it is. If the object is moving to the right and we calculate the force of friction, well, which way is friction acting? To the left, right? Opposite to the way that it's moving. We didn't need an equation to tell us that direction, right? Okay. That's good because this equation won't tell us the direction. The force of kinetic friction is equal to, that's a crazy letter, mu. It's a Greek letter, mu. It stands for the coefficient of kinetic friction. And the coefficient of kinetic friction is essentially a number that tells us how much two materials stick together. The coefficient of kinetic friction between, say, rubber and pavement is somewhere in the range of 0.8. The coefficient of kinetic friction between rubber and ice is somewhere in the range of 0.1. Which two objects stick together better, rubber and pavement or rubber and ice? Rubber and pavement, obviously, right? Okay. The coefficient of friction is higher. Now, the coefficient of friction for snow tires, for winter tires, is higher than the coefficient of friction for regular all-season tires. Right? That's why we want winter tires. It has very little to do with the tread on winter tires. That's not why we want winter tires. We want winter tires because they're made with a different kind of rubber. A different kind of rubber that has a higher coefficient of friction, which stick to ice better than regular rubber that's on all-season tires. So why don't we use them all year round then? If it sticks better, why don't we use them all year round? Yeah, they wear quicker. In the summertime, you don't need them, right? And they wear quicker. So instead of getting 100,000 kilometers out of your set of tires, maybe you get 60,000 kilometers out of your set of tires. Okay, if you're just using them in the wintertime, it's not such a big deal, right? But if you're using them all year round, that's gonna add up. A coefficient of friction, mu, the Greek letter mu, basically how much two things stick together, how much two materials stick together. But it's not just equal to mu. It's equal to mu times the normal force that acts on the object. So if you've got a car rolling down the road, has a mass of 1,000 kilograms, well, then the normal force would be 9,810 newtons. If we multiplied the coefficient of friction, 0.8 for rubber and pavement, by that 9,810 newtons, that would give us the value of the force of friction. Not the direction, okay, but the value, the magnitude for the force of friction. Does this look a little bit tricky? Is this a little bit tricky to you? Not too bad? You know what's tricky to me? Here's a letter in an alphabet we don't even know. The Greek alphabet. There'll be a couple more of those this year. A couple more Greek letters, but not very much this year. A couple more next year. Here's the one that's a little bit confusing. Static friction. It's not equal to any equation. It's less than or equal to the coefficient of static friction, we'll call it mu s, times the normal force. Well, if it doesn't have a specific value, like kinetic friction does, if it's not equal to something like kinetic friction is, then how do we find out its exact value? Okay, when I pushed on Tyler's desk, the force of friction once was 10 newtons. How do we figure out that exact value of static friction if this, we call it an inequality actually, not an equation, if this inequality describes the relationship? Yep. Okay. This won't tell us what the force of friction is. This tells us that whatever your value for static friction is, it's got to be either less than or equal to whatever number this is. This is, right here, your maximum force of static friction. So in the example that I was giving you here a few minutes ago with Tyler's desk, okay, this number, mu times Fn, would have equaled 50. The force of static friction was less than or equal to that 50 newtons. Now, how do I find out exactly what value it was? Well, how hard did I push? If I pushed with 5 newtons, it was 5 newtons. That's less than or equal to 50. If I pushed with 10, the force of static friction was 10. That's less than or equal to 50. If I pushed with 50, static friction was 50. That's less than or equal to 50. If I push with 51, what's static friction? Oh, 0. Because the force of static friction has to be less than or equal to the maximum amount, and the maximum amount was 50. And I just exceeded that. So how do we solve for something in an inequality? Well, the reality is we don't. What we're going to do is change this around a little bit to turn it into an equation. We're going to say the maximum force of static friction is equal to mu times the normal force, the max force. Okay, when I multiply mu between Tyler's desk and the floor by the normal force of his desk and the floor, we get 50 newtons, the maximum force of static friction. That's not the value for static friction, that's the maximum possible value. The value will always be equal to that number or less than that number. So here's what we're actually going to use when we solve problems. This equation and this equation. But be careful, because it's this one and this one that appear on your data sheet. So what you've got to do is remember that, wait a second, this inequality here, static friction less than or equal to mu times the normal force, what we actually want to use, what we actually want to calculate is the max force of static friction, which is equal to this part of the inequality there. Was there a hand up back there? Because this, what we see over here, Javi, is the maximum force of static friction. It's always going to be, think about that, it's always going to be less than or equal to the maximum force of static friction. Okay, the maximum amount of money that I have is the $30 that I have in the bank. Okay, well, the amount that I have in my wallet is always going to be less than or equal to that $30. Okay, does that make sense? So I don't necessarily have $30 in my wallet. I might have 15 or 12 or 29. Okay, but I can't have more than 30. Okay, this side here is the maximum force. It's less than or equal to the maximum force. Okay, we can calculate the maximum force by just setting the maximum force equal to that side. Okay. Now here's a table that we'll quiz you on Monday. So copy that down and memorize those numbers for Monday. And we'll, don't worry, I'm not going to ask you all of them. I'll only ask you for 10 of them, 10 of those numbers on Monday, okay? No, it's not going to be on a quiz on Monday. If you need these numbers for a question, you'll be given these numbers. You don't need to memorize any of these numbers. I've got very few of them memorized because even the ones that I do remember, it's just because I've used them lots, not because I've tried to memorize them. This table gives you the coefficient of static friction and the coefficient of kinetic friction of a whole bunch of different materials. Copper on copper, really, really high coefficient of static friction. Pretty high coefficient of kinetic friction as well. It's, the coefficient of friction between a rubber tire on dry asphalt, which is pavement, 1.2. On wet asphalt, 0.6. Hey, listen. Why don't we use, I got a brilliant idea. Why don't we use copper tires and make our roads out of copper? Then our coefficient of static friction would be so much higher. Wouldn't that provide so much more traction? Yes, it would. Yes, it would. It's a little impractical. That's probably why we don't do that. Okay? It's a little impractical. But it would provide us with much more traction. Okay, much more traction in the wintertime. Sorry? Well, I don't know what the coefficient of static friction between wet copper and wet copper would be. It would be less. It would be less, but I think you'd find that it was still more than on wet asphalt. But it's not practical, obviously, right? Copper studded tires? Yeah. Now I don't know what. Just be careful with that though, because it's a good idea, but I don't know what the coefficient of friction is between copper and asphalt. Like copper and copper is really high. Copper and asphalt might not be all that high. You can get studs though to put in your tires. I don't think they're made out of copper. I think they'd be made of, now I think they're made out of plastic. Like a plastic now, I think. I think so. Yeah, steel ones. When I was younger, people used to put steel studs in their tires to drive on the road. Now I think it's illegal to do that because it's so hard on the road. So they put plastic ones in there now, which doesn't increase your coefficient of friction, but just gets you digging into the ice, right? Kind of like when you're pushing off skating, it just digs into the ice, right? And what's right? And mud, yeah, and mud. Take a look at the coefficient of kinetic frictions. Look at them. They're all lower, right? They're all lower than the coefficient of static friction. It doesn't mean that kinetic friction will be lower than a particular force of static friction. It just means that it'll be lower than the maximum force of static friction, that's all. Make sense? What's this one? Synovial fluid on a joint. That's a really, really low coefficient of friction. Yeah. When I bend my elbow, well, I'm old, so sometimes you do hear some creaking because I'm old. But normally when you bend your elbow or you move your shoulder or you bend your knee, you don't hear creaking, and it doesn't generate a whole lot of heat when you do that, generally. Okay? And it doesn't hurt generally when you do that. Why? Well, you got bone and bone rubbing against each other, right? Well, no, you don't. You actually have a fluid in between the bones that allow the bones to not actually make contact. So the coefficient of friction is reduced dramatically from bone on bone to fluid on the joint. 0.01. That's an incredibly low coefficient of friction. Okay? Slides really, really well. It's amazing how the body does these things that it needs to do, produces these things that it needs to produce to make it work efficiently, right? Okay. Even Teflon. If you had Teflon joints, okay, that wouldn't be bad, but it's not as good as nature made us, right? With synovial fluid. Okay, here's a question. 3.17 on page 185. It says a sled with waxed hickory runners rests on a horizontal, dry, snowy surface. What's the mass of the sled if the maximum force that can be applied to the sled before it starts moving is 46 newtons? And we got to get our coefficients from the table, right? Okay. What are we dealing with here first, though? Is it kinetic or is it static friction? That's what's important first, before we even look at givens or before we look at coefficients of friction here. Are we dealing with static or kinetic friction here? The maximum force before it starts moving is 46 newtons. That's, who said that? It's the maximum force of static friction that we have given to us. Does that make sense? You apply a force of 35 newtons, what happens? Nothing. Static friction would be 35 in that case. Apply a force of 45. What happens? Nothing. Static friction would be 45. Apply a force of 47. What happens? It moves. Static friction is now 0, and kinetic friction would kick in. They're saying the maximum force that you can apply before it begins to move 46. The maximum force of static friction. Okay, let's get the coefficient of friction between hickory runners and a dry, snowy surface. Hickory runners and a dry, snowy surface. That's going to be this one, right? 0.06. Notice there are no units for coefficient of friction. We call it a dimensionless quantity. It has no units. Mass is what we want to find, right? Well, my equation that I use here, we know the static friction force is less than or equal to mu times the normal force, but the max static friction force is equal to mu times the normal force. Usually on a flat horizontal surface, the normal force is equal to what? Doesn't? No, but you're on the right track. Dustin, what's your mass in kilograms? Around 80? We'll say that, 80. 175, so maybe 70 kilograms. Okay, 70 kilograms. So Dustin has a mass of 70 kilograms. He has a force of gravity acting down on him of 70 times 9.81, right? About 700 newtons, 686 newtons, but we'll say 700 newtons. Gravity acts down with 700 newtons. Is he moving down? Is he moving up? Well, if gravity is pulling down with 700 newtons, the normal force must push up with 700 newtons, the same as the force of gravity, right? So for now, the normal force will always be equal to gravity for us. Okay, it's not always going to be later on, but I'll explain to you when it's not. Okay, so for now, we're going to say FSF max is equal to mu times m times g, g being 9.81 meters per second squared. Okay, let's rearrange it to solve for m. Let's take the mu and the g over by dividing. Maximum force was 46 newtons. Divided by the coefficient, which 0.06, I think. Yeah. Times 9.81. Let's do that one on our calculator here, okay? We're going to say 46 divided by, let's use some brackets down here, 0.06 times 9.81. 9.81. And that bracket, we get 78.2. So the mass here is 78.2 kilograms. Now, technically, how many digits should that be rounded to? 1, right? If we look at our data, here's 2 digits. That's only 1 digit. Final answer should be 1 digit. So this would technically be 8 times 10 to the 1 kilograms. 8 times 10 to the 1 kilograms. Does that make sense for people, that question? I'll tell you what the biggest problem people have, recognizing that this is static friction, not kinetic, that we had to use the 0.06 value as opposed to the coefficient of kinetic friction. Okay? Does it make sense why it's static? The force that's applied before it begins to move. Okay, that's maximum static. Kate, question?
So what did you do with the normal force?
What I do with the normal force? Okay, good question. I said the normal force here is equal to gravity, m times 9.81. And the reason I said that is because usually on a flat horizontal surface, the two are equal to each other, right? Gravity pulls down on you with 800 newtons. Normal force pushes up on you with 800 newtons. So the easiest way to find the normal force is to find gravity. M times A or M times G, sometimes we call it. Yeah. Question? Jesse? Got it? Is that okay? All right. This is where we're going to leave off for this week. The practice problems on page 185. So these 2 questions right here. Now, remember, you are going to need that table. Okay, so that table is on page, what is it? Page 183. Take note of that. And when you're working on these questions for homework, refer back to page 183. Okay? That's it for today.